Hello students, today we'll be trying to see uh, what is bipolar junction transistor, what are the terminals of BJT, and what is the symbolic representation of bipolar junction transistor. We do have two types of BJT transistors, which is NPN and PNP. So we'll be seeing the symbolic representation of that. I'll be also teaching you what is the meaning of biasing and what is the purpose of biasing is been done in BJT amplifier circuits. So why do we need biasing to be done in BJT amplifier circuits? And we'll also be discussing some sort of biasing techniques that are basically used in designing the BJT amplifiers. Okay, so first of all, what we do is we'll try to see what are the three modes of operation that we normally do in BJT amplifier circuits. So three modes of configuration you can say, or three modes of operations you can say. So we normally, basically we design amplifier circuits, we design some sort of emitter follower circuit, based on these mode of configurations. So before that, I will just tell you what is the symbolic representation of a transistor and how PNP or NPN transistor symbolic representation is done. Okay, so I am trying to tell you about BJT, so keep that in mind, which is bipolar junction transistor. So it is bipolar junction transistor. So it is bipolar junction transistor. So basically, the transistors are used to create amplifier circuits where amplifier circuits are being designed to amplify voltage or to amplify current, or we also have the circuits, amplifier circuits, which are designed to generate input and output impedances. Okay, so in most of the applications we need infinite input impedance, or we need very high input impedance, and it should, the circuit should show the the output impedance very low. That is one requirement. Also, we need, the input impedance should be very low and output impedance should be very high in certain circuits. Okay, so it all depends on what type of application you're working on, based on which type of amplifier can be used, to amplify voltage, current, or impedance, whatever you are trying to design for. Okay, so basically, the symbolic representation of transistor is this is what I can say, which is the symbolic representation of transistor. So the symbolic representation of transistor is this. And you see the arrow is going out of the base. So this is actually an NPN transistor. Okay, this is the symbolic representation of NPN. NPN means you have a junction. Two junctions will be there here. One is NP and another one is PN. So can you see here NPN? So you have two junctions here. So one is NP and the other one is PN. Okay, so basically, the transistor BJT is made up of two diodes. If you have a single PN junction, we always call it as a diode. If you remember about diodes, if you have a single PN junction, we will normally, call it as a diode. Here in NPN or PNP, any transistors is made of two diodes. One, I can say, a collector diode, okay, a collector diode, and the other one is the emitter diode. The other diode which we have in any transistor is emitter diode. It means that you have a diode between, okay, I think I should tell you what are the three terminals first. Now the horizontal vertical line which you have written here, which normally called as base. So base, B is base, and the terminal without arrow, what you can see is collector, and the terminal with arrow, what you see is an emitter. This is an emitter. So you have three terminals in a BJT transistor, bipolar junction transistor. So one terminal is the collector, another one is base, and the third one is emitter. So as we have three terminals here, we are also marking three current terminals here. One is your collector current IC, the other one is the base current IB, and the third one is the emitter current IE. Always, keep this in mind that the base current and collector current will always flow towards the transistor, whereas the emitter will be flowing away from the transistor. Because we normally write the equation, IE equals IB plus IC. Okay, so this is the actual equation for any transistor. The emitter current will always be equal to base current added with collector current. As the base is lightly doped, base will always be lightly doped. As the base is lightly doped, we normally, consider the emitter current is approximately equal to the collector current. Because when base is lightly doped, we normally see that the base will be very less. The base current will normally be in microamps. Okay, so it is very, very less. So therefore, we normally approximately equal IE and IC are to be equal. Means both the emitter and collector currents are to be equal. Okay. Now coming to these diodes which I was saying, you will have between base and emitter what we call it as an emitter diode. Okay, so we will be having voltage across base and emitter which we call it as VBE. Okay, and we will have a diode between base and collector. Okay, so anyway, we will not be normally considering this VBC in any of the designs. We go with this VBE, which is very, very important parameter in common emitter configuration of BJT. Okay, so I will tell you later what is the three modes of configurations or operations. So I can say it is configuration. Okay, later we'll see, further when I am discussing about three modes of configuration, then we'll see what is common emitter. So in that case, we will be, more concentrating on VB. Now, as I said you, this is an NPN transistor symbol. Whereas when you take PNP, so you will have a base as usual. Both NPN and PNP mechanism is same. But the thing is, your transistor emitter arrow will be towards this direction. Okay, so as the emitter arrow is towards this direction, you normally see that the emitter current will now be flowing towards the transistor, whereas the base current and collector current will be going away from the transistor. So due to which the equation what I wrote here will remain same even for PNP transistor. Okay, either you take PNP transistor or NPN transistor, I equals IB plus IC equation will remain same. Because here the emitter current is flowing out, whereas IB and IC is flowing in. If we write the equation of, you all know about KCL, which is Kirchhoff current law. Kirchhoff current law is used here. Kirchhoff's current law is used here. So when Kirchhoff current laws, what Kirchhoff current law says, the current entering the node will be equal to the current leaving the summation of current entering the node will be equal to the summation of current leaving the node. Okay, so therefore here IB and IC are entering, I is leaving, So therefore, we can generate the same equation. Here IB and IC are leaving, whereas IE is entering. So therefore, we will end up in getting the same equation. Okay. Now, I hope you got the symbolic representation and the current, normal current equation in terms of the BJT transistor. Configuration that have been done when we use the bipolar junction transistor for amplifier designs. Okay, so we normally go with these configurations so that the transistor, which is BJT transistor, can be used for designing the amplifiers for various applications. Okay, so the three modes of configuration which goes with in this way, like first one is, the first configuration is the common, we call it as common emitter configuration. So common emitter configuration, and the second one, this is common emitter configuration. The second configuration, which is common common base configuration, and common base configuration. And the third configuration is the common collector configuration. Now, when I go with common emitter configuration, so let me give you a brief knowledge on common emitter. So, common emitter configuration. So, in common emitter configuration, we see that the input is given to base. Output is measured at collector, whereas emitter is connected to ground. Emitter is connected to ground. Okay. So here, input is given to base means the input is given from base to ground. Okay, from base to ground. Between base to ground, the input is given. Between the output is measured at collector, it means that the output is measured across collector to ground, whereas the emitter is connected to ground. So this is why it is called as common emitter configuration. Okay, so this is the reason why it is called as common emitter in configuration. Normally, these common emitter configuration are used to design, the voltage amplifiers. Okay, so later we'll discuss on, biasing, and then I will be, teaching you how the amplifier design can be done. So there you will see what is the benefit of doing using common emitter configuration. Okay, so when I write the circuit for this common emitter configuration, so we all know the symbolic representation of a transistor, which we saw earlier, which goes with in this way. So this is your collector, this is your emitter, which is which is normally written. Normally, I'll be discussing more on NPN from now, so keep that in mind. Now this is my collector, base, and emitter. So this is base, this is collector, and this is emitter. Now, as I said you, the input is measured across. Let me say this is the ground. Okay, this is your ground, where this is connected to ground. The input is given to base. So this is your input. Between input is given to base and ground, whereas emitter is directly connected to ground. Or sometimes you also see emitter is added with some resistance here and then connected to ground. Okay, so therefore that is also possible. Whereas the collector, between collector and ground, is where the output is, measured, where we measure the output. Okay, so this is where this is how the configuration of common emitter is being done. Okay, so the input is taken across the input is given across the base, output is measured across the collector and ground, where emitter is directly connected to ground, or emitter can be connected through emitter resistor. Okay, so through emitter resistor also the emitter can be connected to ground. Now, if I say common base, I think now you should realize when common emitter is connected to ground. When I say common base, the base is connected to ground and input is given to the emitter, output is measured across the collector. Okay, so I am going to directly write the common base configuration. If I say, I am going to write directly the diagram. So now the transistor can be written in this way. Input is given to the emitter, output is measured across the collector. So now the diagram is, now this is the base which is going to ground now. This is your ground. Okay, and now input is measured, or input is given to emitter, where input is given to emitter across emitter and ground. So this is your emitter, this is your base. Now the output is taken at the collector. This is your output which is measured between collector and ground. So this is your collector. Okay, so this is common base configuration. Now if I go with common, now I hope it is very easy for you to tell for common collector. So if I say common collector, if I say common collector configuration, it's quite simple now. Now the transistor will be what? In common collector, the collector terminal will be connected to ground. Okay, so the collector terminal will be connected to ground. So just right here, the collector, this is the base. So in common collector, base will be the junction where the input is given. Base will be the place where the input is given. So input is given to the base. Okay, and this is ground, where the collector terminal will be connected directly to ground. The output is now taken across the emitter. Now this is the output. This is the output. Okay, so this is the emitter, which is where the output is considered. Collector is now given directly to ground, whereas base is where the input is given. Okay, so this is common collector. Now this is how the three different configurations that we do by using BJT, so that we can design certain amplifiers. As I said you, the common emitter is normally used for voltage amplifier designs. The common base can also be used in the same purpose. Okay, but common collector is normally used. In most of the cases, common collector is very importantly used in emitter follower design. This will be discussed later. I will be teaching you what is emitter follower. Okay, so here common collector is normally used for designing the emitter follows. Okay. Thank you. The meaning of biasing and for what purpose the biasing need to be done for designing the BJT amplifiers. Okay, so the purpose of biasing in BJT amplifiers. Before discussing about biasing, I just wanted to discuss about a DC load line in any BJT amplifiers design or in any common emitter configuration, or DC load line is also written for common collector or common base anyway. So in common emitter configuration, normally we will try to plot the curve for an amplifier circuit which will give us certain values. Okay. Now this is the characteristics. So we call it as common emitter characteristics curve or BJT common emitter characteristics curve. Common emitter characteristics curve. Now what is this curve is actually giving you the knowledge. Okay, so that is very important for us to discuss here. So in this curve you can see something called as a DC load line. Okay, so this is a DC load line which you can see in red in color. Okay, so the red line what you see is a DC load line. Okay, which is been marked in a graph where you have an x-axis which is collector emitter voltage. Okay, so when I take a transistor, for example, in common emitter, this is the common emitter configuration, you will have, as I said, you will have a resistor and then connected to ground, and this is your collector terminal which is connected to VCC, and this is your base. Okay, where base. Now if I go with the voltage across the collector terminal, this is collector terminal, we know it, this is base and this is emitter. If I go with the voltage across collector and emitter terminal, this voltage is actually VCE. Okay, VCE. Okay, and the current flowing through the collector terminal is normally considered as IC, which is the collector current, which I told you earlier. The base current is IB and the emitter current is what we normally consider it as IE, emitter current. Now the DC load line is plotted by trying to take two different values. Always the Q point is located in DC load line. That is very important. Q point is located, Q set point is located in DC load line. DC load line. The load lines are of two types. One is DC and another one is AC. As we are not working on AC till now, as we are not discussing any AC input given to the base till now, therefore I am not discussing anything on AC load line. So most of our discussion will be on DC load line. Okay. So most of the discussion will be on DC load line here. Keep that in mind. So here, when I take a DC load line, as I said you, the Q point is located on the DC load line, where the y-axis will always be IC marked, if you see here, and the x-axis will always be voltage VCE. Whereas this characteristic curve, what you see in the middle of the graph, is actually the current IB is marked. Okay, so IB varies actually here. So IB will vary. So IB varies. Later we'll see when discussing about biasing circuits, we'll try to see equations. So there we'll see how IB is going to vary like this. So anyway, by plotting this curve, okay, by plotting this curve, which is VC versus IC and IB, and plotting a load line, we are going to define three modes of regions, three regions of operation of BJT. We are going to achieve a condition where the transistor can operate in three different regions. The first region is, or the region I cannot say it is first region. Anyway, three regions, out of which one is the saturation, and the another region is active, and the third one is cutoff. The third one is cutoff. Now, this region, what you can see here, is actually a saturation region. Can you see here? A saturation region. A Q point will always be located. The Q point will always be located at the active region. Okay, so this blue color, what you see, is completely an active region. This completely from here to here, what you see somewhere is active region. Whereas at the bottom, can you see this region? This region, what you are able to see, is a cutoff region. Now there are conditions where your transistor reaches the saturation, whereas your transistor reaches to cutoff. Now, when your transistor reaches to saturation is when the collector current IC will be equal to VCC by RL. Then this is the maximum current IC that you are able to achieve when any biasing of BJT is done for a common emitter configuration. Okay, you will be able to achieve the collector current IC, which is equal to VCC by RL. So this is the maximum collector current that you achieve. Therefore, at maximum IC, you will be able to see that the transistor gets into saturation. Once the transistor gets into saturation, we can say that the transistor will behave as short circuit. Keep that in mind. So once the transistor gets into saturation, the transistor will start behaving as a short circuit. At saturation, we also have another value where at saturation, we will be able to see that VC equals 0. It means that the collector emitter voltage is 0. And I think this is very important. Let me tell in this video. When the voltage equals 0, across any two terminal, now think you have two terminals here. Now when voltage across these two terminals is 0, it means that it is short. When voltage is infinity, then it is open. So if you see here the voltage is infinite, so it is open. When it is 0, we normally go with short circuit like this. Similarly, if I go with resistance or impedance, when resistance is 0 ohms, so this is 0 volt and infinite volt, unit is very important, keep that in mind. When resistance is 0 ohms, we normally consider such cases as short circuit. Means, as this is short, you see here, across this, voltage is also 0, resistance or impedance measurement across that short circuit is also 0. When I say infinite ohms, then this is considered to be open. So when I say infinite ohms, this is considered to be open. So it means that when I have a open circuit like this, in that case, we will be able to see that both voltage and resistance is infinite. So similarly, we have one more parameter which is current. When current is equal to 0 amps, then it is open. When I say the current is infinite amps, then you say it is short. Now here in this case, you see V equals infinity, R equals infinity as both terminals is open, but at this place, if you measure current, will be always 0 amps. If I have short circuit like this, then the entire phenomena will get changed. So what I will be able to see is your voltage V will be equal to 0, R will be equal to 0, but the current will be infinite. So why I am saying you this, because when VCE equals 0, it means that this collector and emitter terminal will behave as short. Because voltage is 0 now. So once voltage is 0, it means that the collector and emitter will behave as short circuit. That is the reason at saturation you will see maximum IC current, and that maximum IC current is nothing but VCC by RL. At saturation you will see very low collector emitter voltage, which is ideally we consider it is equal to 0. Whereas when you take cutoff region, VCE will be equal to VCC. VCE will be equal to VCC. Whereas at cutoff region, your current IC will be approximately equal to 0. At cutoff, the current IC will be equal to 0, whereas at cutoff, your VCE will be equal to maximum voltage. See, for any circuit, the maximum DC voltage will always be VCC. For any circuit, maximum DC voltage will be equal to VCC. Okay. So therefore, VCE equals VCC and IC equals 0. Okay. This would be the case for cutoff region. But when I go with active region, okay, now when VC equals VCC means think it is infinite. Very maximum value is nothing but voltage value, which is VC equals approximately equal to VCC. See, theoretically we say it is infinity. Practically we don't have anything called as infinite. Here also, theoretically we say it is 0, but practically it is not exactly 0. It will be some minimum value. Okay. So therefore, as it is very maximum, and we know that when voltage is very high, your circuit will behave as open. That is the reason when voltage VC is very high, so it is VCC now, therefore your CA collector and emitter terminal will try to behave as open circuit. Okay, they both will behave as open. That is the reason the cutoff region is considered when VC equals VCC. Whereas current IC is very minimum. Okay, during cutoff the current IC will be very minimum. That is the reason you see this is the region where you see current IC is very minimum. And this is the reason where you see current is very maximum. And this is the place you see where VC is very high. Okay, so that is the reason you see when VC equals 0, IC equals VCC by RL, you will be able to see the saturation. When IC equals 0 and VC equals VCC, you are able to see the cutoff region. At Q point, now at Q point is considered to be an active region. At Q point, we normally consider it as active region. At Q point, we consider that the VCE, the voltage collected to emitter voltage, will be approximately equal to half of VCC. At Q point, your VCE, which is collector emitter voltage, will be approximately equal to half of VCC. Whereas IC will be some numerical value. Means we don't have any assumption that we make. IC will be some milliamps. IC will be, assume that IC will be equal to some 4 milliamps or 3 milliamps like that. Okay. Theoretically, I can say IC will be either 3 milliamps or 2 milliamps or 4 milliamps. It all depends on the type of transistor we take. Okay, because IC will be mentioned in this, you can see a data sheet of any transistors that you are going to use. There you will be able to see all these values, theoretical, the values for that particular transistor which is designed for. Okay, so these are the three major regions on which the transistor is going to operate based on different, operations for different regions. Okay, so anyway, now we'll see out of these three regions, okay, which would be the region for me to design an amplifier so that it can give you maximum gain. Out of these three regions, which would be the region where your transistor should operate such that it can give you maximum gain? As I said you, if my transistor gets into saturation, it will be closed. Whereas if my transistor gets into cutoff, it will be open. So therefore, if you want to make the transistor to behave as a switch circuit, okay, switching network if you want to create using transistor, then you should make the transistor to operate either in saturation or cutoff. But I am trying to design an amplifier circuit which can give me more gain, either current gain or voltage gain and so on. Then I need to make sure that my bipolar junction transistor is getting operated in an active region. So that is the condition I want. Okay, that is the condition I want. I want to make sure that the BJT is operating in Q point. Okay. Now, this is the major reason why we do biasing. This is the major reason why we do biasing. Okay. So, we do biasing so that, so biasing in BJT is done. Okay. Biasing in BJT is done for what purpose? Biasing in BJT is done for what purpose? So, we do biasing in BJT by providing a necessary DC voltage. So we do biasing which provides so when I do biasing, the biasing will provide the necessary DC voltage and current. DC voltage and current where my transistor will be on. To turn the transistor on, on and and then and then sets the correct Q point, correct Q point, for amplification. One thing I need to tell you, like the BJT behavior, the transistor behavior will also vary in terms of increase in temperature. Okay, so the transistor will also vary in terms of increase in temperature. Okay, for example, for every 1 degree temperature, increase, okay, your transistor will be facing a room temperature, right? So your transistor will be facing room temperature. Now, if every 1 degree centigrade of temperature will change in terms of room temperature, your base emitter voltage, the base emitter voltage VBE, the base emitter voltage which I told you earlier, this will get reduced to somewhere around -2 to -2.5 millivolts. For every 1 degree temperature increase or changes in 1 degree temperature will make the base emitter voltage to decrease for -2 to -2.5 millivolts. Similarly, it will decrease VB also in the same way. Base voltage will also be decreased in the same way. Whereas your collector voltage VC will be decreased somewhere to -0.1 volts. Okay. So even it will affect the current IC, IB, IE also. So these changes will definitely make the transistor behavior in a different sense. So, okay, because -2 to -2.5 millivolts is very, very high because when we design an amplifier circuit by using BJT, the input voltage what we give is very minimum. We normally call it a small signal operation. Okay, so when we normally use very small signal as an input for BJT amplifiers. Now, once the input is very small, like 100 milli or 50 millivolts, like that, these changes in terms of 1 degree centigrade temperature increment. VB is changing to -2 to -2.5 millivolts. VB is also getting reduced to such voltage, and VC is getting reduced in terms of -0.1 volts. This decrement will have a major effect on the transistor behavior. Okay, so this is another reason why biasing is compulsory to be done for an amplifier design. Okay, so once the Q point is set, that is the important thing. Once the Q point is set, all this variation in terms of temperature can be we can neglect those things. That is one thing. Biasing is very, very important for us to keep in mind. Okay, the biasing will also avoid distortion. As I said you in small signal operation, as the input, if you try to increase little bit more, your saturation clipping will occur in transistor. The clipping is nothing but, it shows some sort of square wave when your transistor gets into saturation. Okay, so that is where distortion is meant to be. Okay, so if you do proper biasing, then distortion can be omitted. Distortions can be omitted. Okay, so the biasing will ensure, this is another case, the biasing will ensure that the base or emitter base junction, emitter base junction is forward biased, is forward biased, is forward biased, and collector base junction is collector base junction is collector base junction is reverse biased, is reverse biased, reverse biased. Now, this is very important case that we need. We need emitter base to be forward biased and collector base junction to be reverse biased always, so that the active region is maintained. So that the active region is maintained, and due to active region is maintained, linear amplification is possible. Linear amplification is possible. Linear amplification is possible. Amplification is possible. So this is very important factor of biasing. Okay. Okay, fine. So what we learned till now is what is saturation, what is active region, what is cutoff region in terms of transistor biasing. Where in biasing, why biasing is done, so that the transistor can remain to be in active region for very good amplification or linear amplification. So what biasing does, and how the room temperature and the temperature increment is depending, the transistor is depending on those things. And if we do biasing, emitter base junction will be getting forward bias, collector base junction will be getting reverse bias, due to which the active region is maintained, due to which again the linear amplification is possible. Okay. So I hope in this video you got a brief picture of